I couldn't have imagined a better segue into my talk than Paul's previous talk. So those of you who were around for that one, this is basically a continuation of some of the things that we talked on there. So it's perfect timing. I'm Chris Hazard. I am the founder and person who runs Hazardous software. Some of you know us from the company that made the time travel RTS Acron a few years back. Mostly we work in serious games now, but we do have another, we're working on a few more things for the consumer market that should be coming out next year or so. So you'll probably be hearing about us a little bit more. My background was in, my PhD in particular was in trust and reputation from a game theory perspective. So I'm an AI guy through and through, multi-agent systems guy. So this is my kind of bread and butter stuff. So as I mentioned before, I've been working in serious games for a while. I've done a little bit of business process work in the past. And so what this talk will be is about some things that we've been working on and just some of the ideas that I've had around it about procedural behavior generation. Talk a little bit about procedural content generation. And this talk was aimed a little bit, I wasn't sure if it would be more in the design track or programming track, so they put it in the programming track, so it has some things in it that are more design oriented. So some of you programmers might go, okay, I understand this, but designers will be a little bit new to you. So I'm trying to aim for both crowds here. So one of the things just talking about how do we make behaviors in games now. When I say behaviors, I mean generically. It could be the AI, it could be the game mechanics, and sometimes the two blur together a little bit, especially if you have like a fighting game or something where the opponent's behaviors are very intertwined with your goals. So I use that very loosely. So how do we make them now? Well, scripting is by far and large the number one way we use it. Sometimes it can be little scripts that all work together, big chain of modular interfaces and different components, or maybe it's just a big long script. This is exactly what the enemy does. This is the Mega Man boss that jumps this way, and then back again. Increasingly, we've been seeing a lot of behavior libraries, whether or not it's all the things on the Unity store, or Game Salad is another good example where you have this big library of things that all these objects and entities and rules are built to work with the engine and this type of games. So for example, you might be able to take an AI module and use it in a first-person shooter in that genre, but it might not work so well in an RPG. But they're sort of general, and oh, here, this object floats in the air. It's a balloon. Okay, great, we can put that into the world. But you need that library to begin with, and you need to search through that library, and either you need to find it somewhere else or create it on your own. And the last way, as Paul talked a little bit about at the end, is machine learning and putting machine learning into your AI. It can be anything from, hey, we have this little component right here that does some optimization of machine learning, to the entire AI is machine learning. I saw a talk by Stuart Russell, one of the authors of the canonical AI book that's used across the world. And he had a wonderful system called Blog, which he named before the word blog became coined, so it's impossible to find. But it was exactly that. You just taught the AI how to play an RTS. So those sort of things are out there, and there's many hybrid systems as well. Now, as I mentioned before, we also do a lot of serious game work, particularly with process optimization, process design games. So in working with a lot of these clients, they have these systems that have been developed for a long time. You think back to COBOL. It was a programming language that people said, hey, we can make business people who don't know how to program write code because it looks like English. Not like I've ever spoken. But apparently it looks like English to some people. There's a number of business process languages right now. I should not just say languages, but also tools along with them to help business analysts, actually they're programmers that work for them because they don't quite accomplish what they aim to achieve, create business processes which are really the programming guts behind an organization. If you're thinking about what are the game mechanics, what are the rules of the game, what are the restrictions, what are the reward systems, it's exactly that for corporations. Same thing. The two of the main technologies, there's a handful of them. I'll just cover BPEL and web methods. They're flow language. So BPEL, this thing over to the left here, you can't see it, it's pretty small font. This is Hello World in BPEL. And yes, that's all XML. A lot of these things, because they want to talk and they have all these, they have to go through about 8 layers of different services, and it gets very complicated very quickly. You have these little tools to help you, and you wonder why business analysts can't really use this stuff that well. They can to some extent. Flow, I think, is in some of these GUIs, you can create things that are kind of intuitive, like branch on some status flag or make some connection or process this report. But you really need a programming savvy business analysts in order to pull this kind of stuff off. It's not something, maybe they could make this really flimsy small script, but not something that's meaty, that's something you'd want to be useful for your organization. So still, we have the programmers and the designers, just like we do in games, same thing in business. So I was thinking about this problem a little bit, and businesses spend a lot of money on this. Business process design typically does one of two things. If you're a Coca-Cola, where they have their business process design very well integrated in their organization, they spend a lot of money on it, then it works very well and it enhances your organization. However, a lot of companies, they pour money into it, they don't pour quite enough, and it sinks, it's just this boondoggle. It doesn't ever quite work. So I was thinking, how can we take some of the lessons learned here and problems learned here, and same with games, and how can we put these two ideas together? Now, to begin with, like I mentioned before, we want to enable more people to program. That's kind of a goal that we have here. Anybody here familiar with either Alice or Scratch? About a third of the people. So Alice and Scratch are programming language environments, I guess I would put it as, to teach and enable people who know nothing about programming, particularly kids, but not just kids, how to program and to try to motivate them. As you can see, there's all these puzzle pieces, especially with Scratch. So if you have a for loop and some iterator, those puzzle pieces fit, so you can only put some sort of iterator in the for loop. Nothing else will fit. It's got some little knobs and graphical things. So you're building a puzzle, and it guides you with creating a program. Alice does a very similar thing, not quite as puzzle-based, but it's still the formative and the colors, and oh, this goes here, here's how I assemble it. If you've ever used Lego Mindstorms, they do a similar thing too, where you're chaining together a sequence of events with kind of like Legos, really. And these, they're effective to some degree. They are effective because kids go, oh, well, this is how I do it. It holds your hand for the syntax a lot. But again, we're forcing people to think in the nitty-gritty of the programming. So how do we elevate the developer, so to speak, or the designer, I should say, or how do we enable these tools to the designer without having to think as detailed procedurally? Now, as programmers, who most of us in the audience are, I'm assuming you're in the programming track, maybe not all of you, but like I said, I've tailored this both towards design and programmers. What do we use now for making AIs? Well, hard-coded logic, if I see an enemy, shoot him. Heuristics, and that can be very domain-specific, that if I see 10 enemies, I need to call for backup. Something like that. Search, pathfinding, all sorts of different techniques with that. Constraint satisfaction, which is kind of like optimization, just says find me a solution that fits with all these different constraints that I have. So in some convex hull, if you do any linear optimization type stuff, but we want to find something that works. Optimization, which is not just something that works, but the best thing that works, or something that is within 5% of the best, or just as good as we can get in the amount of time that we have in 100 milliseconds or 30 milliseconds or something. Game theory, that's my big thing. If you've ever seen any of my previous talks, I tend to bring that up quite a lot, using analysis of the strategy of the game as opposed to just looking at how players are playing it. Let's solve the Nash equilibrium. Let's find out what is the optimal strategy, solve a metagame or solve an abstraction of the game, push that out, see how well that works against the detailed mechanics. First order logic, A implies B, and you can use things like Prolog. Prolog, I don't know of any games that actually use that, but you can use those sort of things. And I've seen games that use similar scripting languages. Planning, we need this, then that, and how do we organize these plans? That's a whole other area of research. Bayesian inference, probabilistic reasoning. Machine learning, and that is a whole class unto its own. Paul talked a lot about genetic algorithms, and I'll be talking about that a bit. And there's really a few classes of machine learning that work particularly well that are widely used. Genetic algorithms are a lot of times referred to as your first choice of last resort. If you have a very hard optimization problem that has thousands and thousands and thousands of variables, you don't know what the topology of the optimization function looks like, you say, you know, you could have 10 PhDs work on this for 10 years, and you might get something. So I'm just going to throw a genetic algorithm at it. It won't give me maybe as good of results as that. I won't understand it, but it'll work. It's a pretty good system. Neural networks are in a similar boat. There's always the competition between the neural networks and the genetic algorithm community. Oh, this is better, this one's better. And there's some other technologies too, like support vector machines, and there's a whole other sets of classes. There's even some Bayesian inference machine learning too. That is Bayesian inference machine learning, or is it statistical logic? That's something else. Human modeling. Okay, you bring some psychologists into a room and say, oh, what are the humans behaving like? And let's model that. Let's put that in the game. And sometimes that's exactly what you want because you want it to feel that way. And then the last one is sort of the WAS method, especially. It's used by some indies too, where you don't have the resources to create a really powerful AI, so let's just make the game only multiplayer. And it works, right? It's fun a lot of times. That's the success of Dota. Now, procedural content. Now, I'm switching gears really hard here. So I was just talking about here's how we make AIs. Now let's start from procedural content and follow that a little bit. Procedural content has been around for a long time. The first movie that, for example, used procedural content generation that I'm aware of was Star Trek II, which used it for the landscape rendering. That was back in the 80s. So this stuff has been known for a long time. Fractals. I'll be talking about that a little bit more in a minute. The demo scene in the 90s, if any of you are familiar with that, that really pushed procedural content hard. Because the goal was you want to have something that wowed people, that just, I can't believe my computer just did that rendered that in real time. And oh, by the way, it was also a 6 or 4K executable. And everything was contained in there. Krieger, made by a demo group called Farbrush, this was a really mind-blowing thing. This is what the game looked like. This came out, when was this? About 2003-ish, give or take. I forget the exact year. And it looks kind of like Quake 3-ish graphics. Cool game, cool first-person shooter. Had about 40 to 60 minutes of content, a whole bunch of different types of bad guys, different types of guns, music in the background that kept on changing. Okay. The entire game fit in 96 kilobytes. Everything. Now, how did they do this? Procedural content generation. So we're thinking, how do we abstract the essence of what we want to create here and just paint with procedure? Not with paintbrushes, but with, I just want to create a room like this and make it so. Paint in all the details. And if you actually are playing through the game, you'll see all sorts of like stains on the walls. A lot of the textures don't repeat that much. It's really impressive. There was another group called Project Offset that was doing something very similar that Intel bought out, and then when they changed their processor architecture, they sort of sunk that project. But that was very cool, and they were doing a very similar thing where I still have not seen a game engine that can do what Project Offset could do 5 years ago. In terms of deformable environments, just everything looked very realistic because the textures, you look in the room and you see there's no repeating textures, it's all different modulations, different high frequency and low frequency textures. It did all that kind of stuff. So procedural content is here and really powerful. So let's talk about how we pull this kind of stuff off. Now, procedural content is about taking process and making it into a game for us. So the artist has a lot of power. You see a lot of fractals, and I'll explain that in a second, in procedural content, and that's because a lot of things in the universe are fractals, but that doesn't mean all procedural content needs fractals. I'll start with the fractal ones because I think they're the most intuitive. So this is known as the Cox snowflake. We start with a line, and every time we have a line, we replace it with this shape right there, a line with a little point sticking out of it. And then we repeat that. So we do one iteration on it, we end up with that. Another iteration, we end up with that. And eventually you end up with a surface that has infinite, or a line that has infinite distance, basically. And it's a fractional dimension because it's not one-dimensional anymore. It's not two-dimensional, it's kind of between. There's what's known as the Hazardous dimension. What's neat about this is if you're thinking about game programming, level of detail. If you're a mile away and this is a single, I don't know, it's 4 pixels on the screen, you'll use that first straight line. You don't care about it. But if the player is right up next to it, you might use this, or you might even use a higher iteration, so you're seeing all the detail, or all the curvature, or all the different components of it. If you take what's known as an L system, so we have some sort of more complicated shape, so like a tree sticking up, or like a tree sticking up with 3 branches or a couple branches, and you iterate over that, you replace the line with each one of those pieces, you end up with awesome trees. Companies like SpeedTrees use not just that algorithm, but more advanced algorithms than that, and iterated function systems and this sort of stuff to create the trees where, from a long way, the level of detail smoothly translates in, and you can see all the bark, all the displacement mapping, all the details all the way back out. And again, nature tends to follow that. Some more advanced procedural content, Spore, when Will Wright was making Spore, he specifically hired a lot of people from the demo scene because they knew procedural content inside and out. And I mentioned before, I showed you Krieger. I've seen a demo with 4K, 4 kilobytes, the executable, that had 3D rendering and these robots moving stuff around in a factory to a music soundtrack. Another game that I've been following for a long time, I think it's really cool. It's made by a small indie group part-time. It's called Infinity. It used to be called Infinity Quest for Earth. They are doing a galaxy-sized galaxy. And I'm not kidding. They are having billions of stars in there, and you can go visit. You can land on a planet, go walk around, go walk in a cave, walk out, fly off on your spacecraft, leave the planet, go across the galaxy to another planet, do the exact same thing, and there's no cuts. There's no loading time. That's all procedural content generation again. So as I mentioned before, not all procedural content has to do with fractals, and that's fractals don't make a lot of sense for artificial intelligence. I mean, they can, because if you have different behaviors, if you're looking at, let's say, a culture, and you're making a world-sized world, you want to make an RPG with 4 billion or 10 billion people on the planet. Well, maybe you want hierarchies, you want organizations, you want different people. So then a fractal might make sense, and I'll talk about that a little bit more later and how you kind of fill that kind of stuff in. So let's look at a procedural content generation that is not fractal related, that is not self-similar, that we're not going to zoom in on, and that's a maze. If you've ever tried to make a maze as a kid, so you sort of draw stuff, and you draw it around, you figure out, oh, well, here's my algorithm for drawing a maze. There's a pretty well-known algorithm, there's a few of them. One is known as Prim's algorithm. So here what we're going to do is we're going to say the entire universe is walls. We're going to break a wall and say this is the start. You can break a wall and say this is the end. And then we're going to pick a random wall that's open, or a random spot that's open, break one of the walls, as long as there's not a hole on the other side. Because we don't want to make loops in our maze. Well, you can, if you want, but you might want to have some sort of, some probability for that so the whole thing isn't just one big grid. So then if you don't break through, you break down one more wall. Then you randomly select another point on there, and you do the same thing. There's ways you can optimize this a little bit by having a kind of an open and closed list like you do for A*. And again, this sort of thing is used in roguelike games and things like that. So how do we apply procedural content generation ideas to behaviors? Again, behaviors being game mechanics or AI. Let's talk about a simplified version of Tetris. Here's all the code that you need for a simplified version of Tetris right on the screen. So we'll have the first part on the left is going to be the thing that eliminates the lines. We're not going to care about the 4 lines or getting Tetris or things like that. I'll just say it'll just iterate, and if you have 4 spots in a row, it'll get rid of those. So for every row, if every column is full, then we're going to delete the row, and it falls down. Now notice I'm using sort of a Python indentation there, and I'm doing that intentionally, because we're going to look at this from what's known as an abstract syntax tree perspective. Now here, this controls the piece falling. If it's a game tick, if it's time to move to tick, 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 then we're going to move the piece down. If it's in a collision, then we're going to start a new piece. Again, this is a simplified Tetris. I'm not talking about like you have that little extra tick to move it and things like that. And last 4 are the player's input, to rotate the piece or to move it left or right. Pretty straightforward, pretty understandable. This is something that, even if you weren't much of a programmer, you'd kind of be able to pick up a lot of this. Okay, but we're still not quite there. This is still a little bit lower level than we'd like to be. So genetic algorithms, I will cover them briefly for those of you who weren't in the previous talk. Genetic algorithm is you want to basically breed some goodness. You want to take some objects that have different attributes and turn them to something good, just like evolution from the biological sciences. So you have a population of possible candidates. Most of them, especially when you're starting a genetic algorithm run, they're usually pretty bad. Like maybe they're mediocre at best. So this one, think about different strategies for a first-person shooter. One strategy might be just run as fast as you can all the time in a random direction and shoot if you see an enemy. Another one might be duck under cover and do some different things, and you start to merge these things together. If you think about it from like an image perspective, you have different pixels, and this pixel's green, this one's blue, this one's red, and you can use genetic algorithms to evolve towards a pixel. So anyway, we have some set of possible candidates. And it's represented by a list of attributes or some sort of tree or some form. Usually you wanted a list, but it can be a tree as well. And then we have some measure of the fitness. Is this good? Is this not good? And that comes from you. That comes from what the goal of the game is, the goal of the optimization is, and you need to codify that somehow so it can be run. Then you have some process by which you choose the pairings or the combinations of the entities for the genetic combination. And you can randomize, there's all sorts of processes. Anything you can think of you can use, and there's different benefits and drawbacks to different things. If anyone's familiar with the no free lunch theory, the no free lunch theorem for optimization, that says that if you have every possible problem out there across the uniform distribution of problem sets, all heuristic-based optimizations are equally bad. They're all equal. And it's kind of mind-blowing in a way, because it's like, well, why am I doing this? Well, you're doing it because the data and the problem that you're looking at isn't across the distribution of all possible things. It actually has structure to it. There's a reason behind it. And so most of the optimization algorithms and heuristics that are used for genetic algorithms and different machine learning techniques are there because they tend to help with most types of data that people deal with. So then now we have these two. These are the two that are going to mate. We're going to cross them over. And there's all sorts of different crossover techniques as well. You can just take the list of attributes and split it in half, split it in 30-70. You can randomize it up. You can cut it in different ways. So we're going to take this chunk from this one, this chunk from this one, this chunk from this one. If you're doing a tree, you can do it by attribute matching, and I'll talk about that a little bit more later. So there's different techniques for that. And then lastly, there are other mechanisms too. So now that you've bred these things together, sexual reproduction is really kind of the fastest way of pushing an effective genotype or effective gene across the population. That's why it's so powerful. But having little things like mutation or horizontal gene transfer can also help a little bit. Sometimes it doesn't help, sometimes it does. It depends on your problem set. Mutation means we're going to take some attribute and randomly, 1 out of 1,000, 1 out of 10,000, we're just going to flip it. We're going to change it to something else. And if you have some more attribute-based thing, maybe it's not flipping it, maybe there's some Markov chain or some probability distribution where if you have this choice, you have a green pixel, make it more likely to be a blue one than a red one when you're mutating it. And then horizontal gene transfer is what viruses do. And those recently have been found to be very effective at moving genes across a population as well. So sometimes you can take one set of genes from one entity and just plop it into another randomly. It's not reproduction, it's just boom, that happened. It happens a lot in the bacterial world. The bacterial world is just a sea of genetic soup. It's kind of very fascinating. And then there's some other methods you can use too, like sort of more epigenetic methods or different ways of activating or not activating the genes or the attributes. And as I said, this stuff it's less important than the reproduction, but it still can be very useful. Genetic programming is a type of genetic algorithm where we're using the genetic algorithm for code instead of just attributes. This has been it is a very difficult area of research, but there has been a lot of research on it in the last number of years. Back in, I want to say about 98 or so, there was a group that was running genetic programming on some algorithms for some FPGAs, the chips, programmable chips basically. They were looking at, I forget exactly the problem they were looking at, but they ran and they said, we want to get a really fast, really efficient chip out of this. So let's try genetic programming. Let's let the genetic algorithms in the program. And so they ran it, and they're getting quite good results from the programs. And because they're genetic algorithms, you can't really see what they've done to the code. You can't take the code, disassemble it, and go, oh, that's how it works. It's really complicated. That's one of the drawbacks of genetic algorithms over some other machine learning algorithms. But it's a trade-off between the different algorithms. Anyway, they're looking at the performance of it, and they're like, oh, let's try this on let's run this on a different chip. They ran in their chip, and it didn't work at all. And they're like, huh, that's weird. So they did a lot more experiments, and it turned out that if they even changed the temperature of the chip, it didn't work. More research found that it was using crosstalk between the wires, so induction between wires on the chip that they didn't even think was possible, and was using that to communicate. So as Paul talked about in his previous talk, where this genetic algorithm found a bug in his balancing that he'd never thought existed, it can do that sometimes. You can't count on it. You can't say, oh, let me run this genetic algorithm and it'll solve all my problems. No. But it can sometimes find things that you were not expecting. So you have to be careful about that too, especially if you're building an AI for the player to play against, and now you've optimized it, and if the player does this one thing, it'll steamroll over them. So again, be careful with that. Okay, so how do we represent program code in a way such that we can use genetic algorithms on it? There's two main ways, and one of them is called, one of them is basically turning into machine code into a string, and the other way is looking at the abstract syntax tree, or the parse tree. There's some nuanced difference between what those two are called. Let's just call it the abstract syntax tree for the purposes of this talk. It's simpler. The abstract syntax tree is looking at the program from the hierarchy, the way in which it's executed. If you're thinking about a tree, it's the in-order traversal of the tree, or pre-order, depending on, I guess pre-order. So we're going to go down and we're going to add two things, but we don't know what they are yet. We're going to subtract something. We don't know what that is yet, but 2.2, let's take that. And from 2.2, we're going to subtract, divided by, x. So we're going to take x divided by 11, and then we're going to take 2.2, take that away from 2.2, and that's how this works. This is really basic stuff with compiler design. All compilers take your code, translate it into this, and then before they work on the lower levels, like the intermediate representation and the low levels. And this is how you parse code. So we can take this, and now we can use genetic algorithms on this tree. So if we have two trees, now we can do different tree matching and different graph matching algorithms to pull them together. And further, so my company is working on some products along these lines. We've got some of our secret sauce or proprietary stuff, but just saying that you can use different annotation methods to help the tree matching algorithms and the graph matching algorithms to accomplish the merges and find out where the commonalities between these different things. The other technique is using something like what's known as the /A language, which is, granted, these things aren't, this is still a relatively new area of research. Well, not that new, but it's still in its early stages. It's been around for at least 20 years, if not longer. /A is a machine language, like the language that or assembly language that your processor kind of runs before it translates into microcode. It's the individual instructions, but it's specifically designed to be easy to use from a genetic programming standpoint. Anybody who's familiar with the JVM, the Java Virtual Machine, knows that it's a stack-based thing, so you're not dealing with registers, you don't have complicated things like that. Oh, we're just going to take this value, push it, take this other value, and then we're going to add the two values. And that's the way these sort of languages work, like /A. So as you can see, we're going to take something in, we're going to zero something, save it, very low level stuff, and add it, and then spit out the addition of those two numbers. Now what happens if we do the crossover, if we do these different algorithms on code? Let's look at a slightly silly example from the Tetris example before. So we have if input left, I hit the left key, then we're going to move the piece left by 1. We're going to subtract 1 from that. That was one of our initial rules. If we're going to input rotate minus, we're going to rotate it counterclockwise, then we're going to rotate the active piece 90 degrees. Now if we cross those over, as I mentioned before, we're going to take one part of one part of another, mix them together. Now we might have if this is just one possible example, remember the crossovers can happen in different ways. If we input rotate, then maybe it'll take those two together. So it's not only just going to rotate at 90 degrees, but it's also going to move it to the left one. Or maybe instead of, if you hit the rotate key, it'll just move to the left one. All those different combinations were possible outcomes of this crossover. Depending on the particular crossover algorithm that you're using. Now, let's say that we have a mutation or maybe a user manipulation on this result. The player says, or the developer says, oh, I mashed these together. That's kind of silly. But there's a neat idea out of that where if I have another key, I'll have input rotate plus. Then I can have the player rotate the piece even further, maybe something that's not 90 degrees. This is where bizarro Tetris. And we're also going to move it to the left one. So that would drastically change the game. That would be some sort of very new behavior. And you need some sort of collision model as opposed to just a tile-based system to model this. But again, if you're using this sort of procedural behaviors, you want to have a very rich environment in which to build upon so that the things mush together nicely. Because whenever you deal with genetic algorithms, the more state space you have and the more flexibility you have in the environment, the cooler results and more surprising results you can get sometimes. The reason for that is because if you have a very constrained environment and just like you can have this state and nothing more, then genetic algorithms will try to optimize, but you may not see the quote-unquote creativity from that. Now, as I mentioned before, what if we put the designer there? What if we put the human as a fitness function? One of the powers of genetic algorithms is that you can run it and you can walk away for the weekend, have your server farm run the game or whatever, and come back and go, oh, this is a pretty good AI. Sure, I'm going to play against this. But that's a blind, mostly blind process other than your fitness function, because you have to take everything that you know and everything that you want and put it into some function that evaluates the goodness of everything. So you come back and like, oh, let's see what came out, and like, oh, I didn't really, that's not what I had in mind. The fitness function, do what I mean, not what I say. Everyone wishes that a computer had a do what I mean button or do what I mean instruction on the processor, but they don't, not yet. So what if we use the human as the fitness function that can change things and go, well, now I'm going to change my fitness function. Now I kind of like this. Let me go with this. Let me use some of my own creativity with it. Let me augment that. And this is an example of, there's a number of groups, mostly researchers, but a few just programmers/artists who are taking genetic algorithms and making art out of them. There's one thing, well this is one example. There's a number of examples where they use this human-guided evolution. Here's a kind of randomized piece of art that the genes encoded to render this particular configuration. And here's another one, and here's 40 more. You go through and you're like, these kind of suck, but hey, this one's okay, and this one's okay. Let me breed these two together. Oh, let me breed this one together. And you do that 30 generations or so, and you end up with some pretty cool stuff. This particular example was a person trying to make a spine. And they just took random shapes, mashed them together, and they were able to get that out of it. No modeling experience. They just like, this looks like a spine, this looks like a spine. They didn't need to define what spininess was, and it didn't take them that long to do either. Because we're good at looking at different things and good at feeling out different things and saying, these are pretty similar. Granted, it is difficult to hit your target exactly. So using these type of techniques, it'll take you a long, long time to get an exact spine model out of this. But you can get something very close pretty quickly, quicker than you might imagine. One of the fascinating things from biological studies is they found that, generally speaking, you can get a very drastic change in a species in just 10 generations of reproduction. And almost speciesization in that many generations. Really, crossover is a really powerful function. So what are some of the notes about implementing this kind of a thing? Well, for one, if you're going to use this, you're going to use these technologies, you want to make everything available. As I mentioned before, you want some sort of fuzzy world. If you're making a Tetris game, you want overkill. You want a full collision engine in there because maybe the genetic algorithms might use that. If you're looking for creativity, that is. If you're just looking for optimization, then you don't want that. If you have a pathfinder, if you have a optimization engine, if you have all sorts of AI tools, you don't need to throw those away, and you may not want to throw those away. You want to make those functions. You want to build those in as primitives for your abstract syntax tree, for your make that available when you're evolving these different AIs together, because it'll just make things faster. Because you don't have to, otherwise if you don't have those, now you don't just have to evolve the behavior, but you also have to evolve the pathfinding, you have to evolve the target acquisition, you have to evolve all these different pieces, but if you have them, use them. This is that modular approach that I mentioned before, where we're going to use what we already have. And then decide which, and this is tricky sometimes, decide which behaviors and attributes go where. Now, gravity. Think about that. Where do you assign gravity when you're building a game engine? Is gravity a property of the world? Is it a property of, well, it depends, right? If you're making a first-person shooter, maybe it's just this ambient thing that is everywhere. But what if you're making a game like Planetary Annihilation, or you're making a game like Mario Galaxy? Now gravity, there's not a down. There's all these different objects that have different gravities. Or what if we just take a different approach to it and say that either mass has gravity, which is what the real physics is, or we say that the objects in the world are the things that have gravity. So if I want to take gravity off of this, maybe this object, we're in some sort of, we're in some genre or some narrative where gravity might not work all the time. So we just take it off of these different objects. We're in the Matrix, we're in Inception or something like that. So now we want gravity, instead of it being a property of the world, we're going to have it a property of every single object. So if we breed things together, some of them might have gravity, some of them might not. So it can be a really nuanced and tricky decision to make, especially if you want to make an AI that can apply to many different scenarios or a few different games. Another thing is you have these powerful genetic algorithms like, wow, I want to get to town and I want to give my designers all this stuff. I don't have to program AI ever again. No. As I mentioned before, you have these different, if you're making the artwork and you're trying to make that spine, you need these random different visual things to mash together. That's fine for visual stuff, but the state space, the number of possible programs that you can write for something that does a little bit of something is so much bigger and so much harder to recognize and so much harder to get something right that you need to, as a programmer, you need to give your library a good head start. You can't just use random programs. Well, maybe you could, but your designer will be sitting there for weeks and weeks trying to get these things to work together and going, I have no idea what's good and what's not. So you need to have written in whatever language or platform that you use you're going to mash these programs together, you need to have a library of behaviors that are at least decent. You don't need to spend a lot of time, but just the designer can go, oh, okay, I want this guy. Here's an enemy that is very aggressive, and here's an enemy that is very stealthy. So let me mash them together and let's see if I can get an aggressive, stealthy one, and let's see what comes out of that. So maybe it's one that is aggressive and then stealthy, or maybe it's just a really fast, stealthy, like, wow, that's a really cool way. It's running underneath all these barriers, and this is the last boss of the game now because it's so difficult. Now, many studios are doing rudimentary versions of this, and I say rudimentary because they're not actually using genetic algorithms. They're kind of doing a genetic algorithm process. So if you have this, you have Joe over here, he wrote this module, and that works pretty well. You have Bob over here and Carol, and they wrote different modules for the AI, and they wrote their different pieces if you have a large team for a AAA game. And the designer might say, we want a character to behave like this, and we don't have anything like this in the game yet. We want to add this new bad guy. So they go, oh, well, we've got code over here, we've got code over here, and oh, I just searched on the Unity App Store or the Unity Script Store, or I searched on this other thing and I found this other library. Let's mash them all together. So people are doing that, but it's not automated. You have to actually write the code and the glue between those different libraries. So what we're talking about here with the genetic algorithms and the genetic programming specifically is developing those seams so that the designers can take those things already done and mash those together. And again, the next step for this is bringing it out of the hands of, like I mentioned with the business process folks, we need a programmer to do everything for us. Here's an idea I have in my head, and especially if some of us have worked with some certain designers that will go unnamed, they have these great ideas and then 5 minutes later they have another one. And as Paul mentioned, programmer time is very expensive compared to pretty much everything else, every other time in the games industry, every other role. Another thing is make sure you don't overtrain on the wrong stuff. We mentioned that genetic algorithms are great for finding these weird edge cases. Make sure that you notice if that's happening. And let me give a little personal anecdote here. When I learned how to play Go when I was about 19 or 20 years old, I learned from a guy who was kind of a mentor for me for like a month, but then he had to move off to a different state for a different job. And I'm like, wow, this is a really cool game. So I started playing, and he was quite good at Go. And he taught me a lot in that like couple weeks. So I tried to get all my friends to play Go. I'm like, hey, this is a really cool game. So they played me, and they only played me a game here, a game there, so I didn't get to play that often, but I played, and they wouldn't play me repeatedly, but I'd play a new friend, a new friend, a new friend, a new friend. And after I'd been doing that for about a year, I came back, and one of my friends who I'd played a year prior got into the game a little bit, and I had played more Go than he had, but he just blew me away. It turned out that I had gotten really good at beating beginners at Go. I got very efficient at that. But I basically had to spend 6 months learning how to, or unlearning everything that I learned because none of that stuff worked against anybody who knew what they were doing. The same thing can happen here. And that's not just a thing of genetic algorithms, that's a thing of all machine learning in general. So regardless of what technique you use, make sure you're careful not to overtrain. There are some techniques you can do to help against that. If any of you have seen my talk on information theory, applying that to game design, use information theory entropic measures to measure the length and the complexity of the code. And you can even, if you're having an automated fitness function, or even if you're not, if you have a person, you can say, here's the complexity of this code. When that number gets really, really, really high and you're not getting much additional behavior, the odds are that you have one of those weird edge cases deep in there somewhere, keeps on going up and up and up. So you want to balance that. A lot of times there's what's known as the C4.5 algorithm in machine learning, which is very powerful. It's a classifier that asks, we want to say, what type is this? What type of object is this? And how do we ask the fewest number of questions to determine what it is? If you've played like those 21 question little game things, you played Guess Who as a kid, where you're flipping up and figuring out, well, does the person have a big nose, or are they wearing a hat? Those type of questions. What's the fewest number of questions you can ask? The C4.5 algorithm is exactly that. It figures out what questions you can ask that give you the most amount of information. And it does that by, again, information theory, by pruning that down. So you can use those sort of techniques as well. The most important thing, and I'm not going to go in this very much because this is a lot of our bread and butter, is that the interfaces are exceedingly important when creating a genetic programming environment. And when I say the interfaces, that means that you have these, I was talking about these different modules of behaviors. How do they mesh up? How do they align up? If you take the traditional approach, and let's say you're writing it in Java, which I would highly recommend against, where you have these big interfaces and you have 5 developers in a meeting and you've spent the entire day defining the interface. Now you go break off and now you spend another day defining the interfaces between your own groups. That way will not work. That just sucks bad. You want to have lots of defaults, lots of ways that these functions that this function really should not mesh with this one, but you know what? If you do, it's not going to error out and it's just going to do something. That's the kind of behavior you want. You want to go so weak typing that your arms fall off. And that's how you need to approach interfaces. So for those of you who are not familiar with the strong typing versus weak typing, strong typing is Java where you need to say, this is the type and I want to cast it to this type, and you end up with lines of code that are about that long. And the opposite is, for example, Perl, where I'm going to use this as whatever type you want and it doesn't care, it'll change it for you. So you want to go as far in that direction as conceivably possible. And then also state is important too. That's a big one. Where is your state kept? How important is it? That's another thing that's some of our bread and butter that we've worked out, but that's something that you really need to think about. Where is that state stored? And what is an instantiation? Like, how do we deal with these different entities? If we have different objects in the world, does the position matter? If you're, let's say you're making a game that is let's say a Supreme Commander type game where you're dealing with vast levels of scale, or let's say a planetary annihilation. We're talking about gravity again. If you're high up in the atmosphere, your gravity is a bit different. So and maybe when you get out into space, your wings don't work anymore. And there's different phase transitions between the different game mechanics. Where is that state maintained? And is that important for your evolution? But then that also delves into what environment are you breeding these things in and where you're testing it. So you need to make sure that your test space, when you breed these things together and your designer said, hey, I have this great game mechanism, look at it, it works. And you're like, yeah, that works in that one level of the game, but not in the rest. Like, it does not work with the ice level because the character his fire feet melt right through and he dies every time. So just things to keep track of. Let's take it up a notch. Now let's take procedural generation for culture. Again, say you want to make your world-sized world of 8 billion people in an RPG, and you don't have the capacity to make 10,000 cultures, because that would take a lot. That would be a lot. How do we make something that's believable and populate those worlds? You saw I mentioned before that Infinity game. How do we populate those with all sorts of different people that, oh wow, this is a culture I'd never anticipated before? Well, first off, we need to look at what the social structures are of people and things in the universe. There's there's a lot of different classifications, graph theoretic classifications for these types of social structures, but two of them to look at that are really important are what's known as a small world network and a scale-free network. A small world means that I've got some number of buddies, and I can send a message via a certain number of hops. As you can see there, it's kind of a ring topology. Like, everybody has a few friends, and you can send a message, boom, 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 all the way around. On the flip side is a scale-free. Scale-free means that there's some really big, beefy providers that I know everybody, and I'm the one in charge, and it trickles down to the smaller people. But the more important, more powerful, the more attachment you have, the more your capacity is. Think about the internet. The internet is oftentimes, you can't prove it, but it's argued to be a scale-free network in the sense that you have your level 3, you have all of your tier 1 providers. They have these massive, massive pipes, and there's only a few of them. And then you have your home PCs in the very end of that graph. You have lots and lots of those that have little tiny pipes. So how do we create, well, these are two different types of networks. The way you create a small world network is you make a ring lattice. You take all your nodes, all your people in your world that you're going to populate. You put them in a ring, and then actually a lattice, I should say. So there's a few connections. And then you randomly rewire a few of them. You say, hey, instead of being friends with this guy, you're friends with this guy instead. And same with you, based on some probability. That's how you make a small world network. That's a nice, now these are just particular algorithms. This isn't the only way to make them. The way to make a scale-free network is you're going to start with one guy, and you're going to add another guy, add another guy, add another guy. Every time you add a person, that person, you attach them to the other nodes in the graph based on the number of nodes they already have. So it's a probability function. So if you're really popular, I'm more likely to connect to you than I am to connect to somebody who's less popular. Another really fascinating study, a lot of people feel that, most of my friends are more popular than I am. That's true. That is true, mathematically speaking. Because if you look at the cross-section of this type of a graph, most of the connections that you have are more popular than you. It's kind of a mind-blowing revelation. If you search for that, there's a paper out there, but it's kind of a neat thing. These are these two types of networks. Now, granted, sometimes they mix together. Like nothing is a pure, it's rare to see a pure scale-free network or a pure small world network. They're usually somewhere between, and there's other properties too. There's exponential networks, there's a whole zoo of different types of graphs. So maybe you don't want to use these exact algorithms, maybe you want to start with these algorithms, mash them together a little bit, come up with some different things and say, well, you know, if we have this culture, throw a heuristic in. This culture tends to operate this way, this culture tends to operate that way. And then you can use that sort of stuff to, if you have these genetic algorithms, you have these different procedural behavior generation tools, now you can use that to start from these social networks, start from the culture in the world, you can do migration flows, things like that, and then push those down and actually get different behaviors out of these different entities. So all these things, I talked about them, I want to see them in games, so please go make them. But they're all starting to become possible, especially given a lot of the mathematics and a lot of the research in the past few years. So in conclusion, make these games, I would like to play them. And I think that procedural content will improve not just productivity, improve productivity of artists. Every artist nowadays uses these Max or Maya or whatever. They use procedural content generation for stone, for all these different types of techniques, for different materials and fabric and things like that. Why not make it for AI? There's some folks at George Mason University that are working on this, like Sean Luke. I know some people at some other universities that are working on this, getting some really good results. Let's take this sort of stuff from academia and move it into the games industry. It's very doable, and I think the ideas like procedural cultural generation are doable and fun. So with that, I will take the floor for any questions.
Make sure you repeat the questions.
Sure. Yeah. I can put it online, yeah. Yeah, if you search for my last name, for my name, I'll be the first link, and I'll hopefully have it up there by next week. Sure. Yeah.
Do you think one of the big things that will sort of make developers hesitant to do this kind of thing, at least in a front-facing that something that's actually the user interacts with, just the absurd unpredictability of it, and that worry that even if you're in testing, it seems to be working really well, but that the users are going to hit some cases just, that really freaks them out or puts them in a state that has a negative effect on the game.
Well, you need to define who the users are. So if you're saying, well, let me do this, and I'm going to release this mod tool with my game to the public right at 1.0 release. If that's the focus of your game, and we're working on something along these lines, then that's fine. If that is your focus. But if you're making this tool internally, and you're like, hey, designers, play with this tool, see what you think. Your customer. It's somebody who's probably sitting a few desks away. Well, if you're working at certain companies, maybe in a different studio, unfortunately, but somebody that you're in close communication with, ideally. Or you can at least talk to your boss and like, hey, let's set up a meeting with this other guy because we have a thick bureaucracy. But it shouldn't be, you're not going to be dealing with a mass number of customers. It should be a handful of designers in your studio. So, and this is also a very cool, fun problem, and I know programmers, we like to work on fun problems, so it motivates us. And doing something like this, even if it's buggy and you have to do a little bit extra support, as long as your boss or project manager or producer is okay with this sort of stuff and thinks this is good for the game, then I think you'll get a lot of buy-in from that. And your customer space, I think, will generally be manageable. Depends on your company.
So do you think it's something that will more commonly used internally to kind of find a good solution, that it will be something that would end up actually being in like a final product, the AI actually learns from the live player? So give me things like StarCraft or something, where you could set difficulties for an AI from like easy to very hard, and is it something that maybe in the future we'll start seeing like a human or some label for a special kind of difficulty where you're going to get kind of randomness because you're trying to learn from all the players?
Okay, so instead of repeating that question, I'm just going to answer it and make sure that I cover the whole thing because that was kind of a long question. So do I think that, well, I guess I will repeat it a little bit. Do I think that these sort of things will actually be used in games or just internal tests? Well, one of the nice things, especially if you use information through, you use different metrics to keep the size of your tree down, the code is still readable. That's one of the magic takeaways from this. And the C4.5 algorithm that I mentioned before, it's a classifier, machine learning algorithm, but you know what? You look at the results of that, and if you keep the tree size small enough, which is a parameter, it's tunable, you go, oh, this makes sense, and you can read it, you can understand it, as opposed to pure genetic algorithms where this output is this long gobbledygook thing that I have no idea how this works. Granted, you can end up with that with these techniques. Don't get me wrong. But it will be a little bit more readable, especially if it's annotated. You have different ways of, when you merge the trees, like this does that, and you keep the annotations when you do the combinations, then it's something that you can actually use in production. You can say, hey, this tends to work really well, and look, I can read this code. I know what it's going to do. Maybe you take a day or two to go through and comb it over to make sure there's nothing weird in there, or even to add a few of your own augmentations and heuristics. But I think it's something that you could definitely ship, especially if you're using whatever scripting language you use for the engine and shipping that, and you use that for your backend for your genetic algorithms and your actually genetic programming, I should say. Yeah.
So I found this really interesting, and I don't have a whole lot of experience in the games industry, but I'm curious as to how exactly this would play into the game development process. Because I would imagine, much like most of the game, is pretty planned. The game is pretty planned out, game design docs and everything, and they kind of know what they're going for. So it seems more like an R&D type of venture than well, this thing needs an AI, we don't know what to give it, so we'll just program a basic one and then match it up to something interesting.
So the question was, when is this going to be used in the production cycle? Is it going to be used early in R&D before the game is decided, or is it going to be used during the game design phase, or maybe even later if you have it in beta and you're realizing, this part isn't that fun, isn't as fun as we thought. Let's iterate on this a little bit. I think it could really be used everywhere, and it depends on the company too. Some companies have a very waterfall process. This is the IP, this is the game mechanics, this worked really well for the previous one. We'll add these 2 little changes because we don't want to take risk, and we're going to ship this game. Other companies are a little more open to that. Other companies are on the other end of the spectrum. That game company, I've got a few friends there. They keep on iterating. They're like, let's throw this game mechanic away. Let's throw this game mechanic away. Let's throw this music away. Let's start over. And they're working towards that really artistic, creative appeal. And it depends on the bottom line is how much funding do you have and how much time can you spend doing this? How much stuff can you throw away? How much time can you iterate? And it also depends on the business model of your studio. So I think it could be used, and if the stuff it ever takes off to be widespread, will be used in different phases depending on the particular organization and the particular needs. Yeah.
Are you aware of any projects that are using the modulating open world games?
So the question is, am I aware of games that are using the network techniques that I mentioned before? I've done a lot of research on this. Like when I was working my PhD, I did a postdoc doing this sort of stuff for real world trust and reputation gathering for the Army on the battlefield. So this sort of stuff is used in research, but I would guess that there are a few games out there that use it, and I can probably, if I spend a few minutes, I could probably think of maybe this game uses it, maybe this game uses something like this, but I don't know of any for sure that I could definitively say that, yes, this game uses this technique. They're common enough, like preferential attachment models like the BA construction, that if you search for Google a little bit, you'll find it. So people who might have had a class in an undergrad might have come across it. So I'd expect that a few people are at least aware of this kind of stuff. Any other questions? We have time for a couple more. No? All right, with that, I'll thank you for attending.